distribution, so Maxwell-Boltzmann distribution goes like e to the minus k, let's see, kBT over En.
Chapter 3, you have that?
Yeah, and this goes, so the fermions, these are the fermions, the bosons go like 1 over e to the En over kBT minus 1, and this is 1 over e to the En over kBT plus 1. All right? And so what this is these numbers are the number of particles, the probability, or number of particles with energy En at a given t. So this tells you the probability of finding a particle with a total energy En at a given temperature. All right? And if you look at these distributions, they go like this. This is the classical distribution. This is the classical. All right? For bosons, it looks like the classical.
It's just got 4 times the...
But it goes like this. It gets higher.
Yeah.
So the classical kind of goes like this, but the boson one at 0 gets higher. So there's a chance at lower energies of having more particles in the lower energy states, and that's what the Bose-Einstein condensate is. And then for this one, it looks more like this. It looks like this.
Right, because when the exponential goes to 0, you get 1.
Well, it means you have a finite number of particles that you can put in a given energy state right there. Okay, and I'm glossing over this stuff. We did it in modern. It's very interesting, and we can get this in terms of the Fermi energy as well. All right, but the scoop is, again, at low energy, the Bose, this distribution, the Bose-Einstein, says that you can have more particles in a lower energy state than you can with the classical distribution. And then for fermions, you have a finite number at 0 energy. All right, and just so that, how do I remember this, guys? Bosons. All right, this is stupid. How do I remember it? But bosons, it begins with B0 or boo, right? And boo is bad, so it's minus. So bosons always have the negatives. So the distributions are the same. It's just the boson.
I remember it because Dirac added to the Schrodinger equation.
Okay, there you go.
Dirac plus.
Okay, so that's really nice, and I'm not going to get into that in any great detail, all right, semester. Okay, the next thing I want you to do is change to section 5.12. So section 5.12. And it's called the exchange force. Okay, and here it is. It's 2 particles. So 2 particles, but only 1d. So we're not talking about a wave function of 3 things. So what we're doing is we're saying that psi, for the 2 particles, psi classical, equals psi a of x1 and then psi b of x2. So this is the classical wave function. All right, and then what we're going to get is for the boson, psi plus equals 1 over radical 2. That's just a normalization. And it's going to be psi a of x1, psi b of x2, and then it's going to be plus or minus for the bosons here. Okay, here it's going to be plus, so it's going to be psi a of x2, psi b of x1. All right, and then psi minus is going to be 1 over radical 2, psi a of x1, psi b of x2, and then minus psi a of x2, and then psi b of x1. Okay, so now, consider 2 electrons. So here we've got like here's electron number 1, and here's electron number 2. All right, if I had to write down a Hamiltonian for this thing, right, a Hamiltonian would include a term like a repulsion. And that repulsive term would go like K E squared over x1 minus x2. Right? So here I have something like this. This is x1. Oh, it's only one-dimensional. It's one-dimensional problem, so it'll look like this. Here's x1, and then here's x2. Okay, so what I'm going to do is I'm going to completely ignore this. All right. Now, normally, if you completely ignore this, right, you have no repulsive term, then there's nothing here that's going to, make these electrons come any closer together or any further apart together, right? There's no interaction between the two. All right, so what we're going to do is we're going to see what happens here, all right? And we're going to ignore this, and we're also ignore spin for now. And this is a big, big thing right there. Okay? So what we're going to do is calculate the expectation value for the relative position, the separation distance. So we're going to look at the expectation value of x1 minus x2 quantity squared. All right, so what is that going to tell us, guys? It's the expectation value of the square difference between where x1 and x2 are, right?
So if you get the expectation of their
distance apart, right? And right now, I'm not including the repulsive term. And so right now, you don't think anything's going to happen. All right? Okay, so what you do is you calculate it for psi classical, psi plus, and the psi minus. And again, I'll call the plus one the bosons, and the psi minus fermion. But we have to be careful, okay? Because there's going to be a complication here, all right? And so what happens is if you follow through with the book, all right, they do it for the three different types. What you get is the following. You get, and so guys, go through this. I was going to go through it, but it'll take way too much time. So x1 minus x2 quantity squared, and he calls them D for distinguishable, but I'll just call it C. This is what I call my classical, and it equals whatever the expectation value of A was squared, plus the expectation value of B squared, all right, minus 2 times the expectation value of A times the expectation value of B. Okay, so that just tells you, you go through and you say whatever the expectation value of A was originally, whatever the expectation value of B was, minus that quantity.
Quadratic.
Yeah, I mean, you go through and you do it. I want you to follow through and do it. Okay?
Put a triangle.
Okay, what now?
Looks like a triangle in the form.
Okay. I'll follow through what he has, okay?
I just mean just that for a second, and all this.
Okay. So now, the whole scoop is, when you do it the next way, you get the following. You get the same thing, you get the expectation value of A squared plus the expectation value of B squared minus 2 times the expectation value of A times the expectation value of B. All right, but then you also get this other term. You get minus plus 2 times the absolute value of the expectation value of AB quantity squared. So all of a sudden you have this new term. So this is new. This is new. everything was the same, everything was the same as before. So this is the expectation value for, the minus goes with the plus, the bosons. So this goes with the plus, the bosons. And then the minus. Okay, so the plus, so the answer for the expectation for bosons is minus this, and the expectation for the fermions is plus. All right, and here, if you go through everything, the expectation A, B is defined as the interval of x times